Okay, now let's take a look inside the capillary and let's analyze more on the zeta potential that we covered in the last part here. So as we talk about, this is the cross section of the copper, capillary, and inside there we have a solid support, right? The surface we call the stationary phase. We have the fused silica capillary with exposed SiO minus group here, the silica group here. Now the silicate here, you know that if it's an oxygen minus charge, is able to attract either the cation, right, in the forms of the H plus ion or the other kinds of cations inside any metallic ions. The thing is, it is very sensitive to the pH, as you know why, because the lower the pH, the higher the concentration of H plus, the more likely that this silicate will be protonated and forms your silanol group, which is a neutral group, right? Now, so you know that this, because of the sensitivity of this capillary towards the pH, it has the effect on zeta potential. Now imagine if you have a low pH, right, such that all these are silanol group, because it's neutral here, would you still have a larger amount of this diffusion layer? Okay? Or the other hand is when you have a very high pH such that most of these oxygens are deprotonated, so it's a O minus charge. This is where you see a very rigid cation, right? This layer here, which is very rigid, and then after that you have a more mobile diffusion layer, and that causes the zeta potential to be lower, like just in the previous diagram here. Okay, so you notice that because it's very far from the negative charge here, you might think that it's just flowing naturally, right, due to maybe energy, but the thing is because they are on their own, they're still charged. So in the two terminals, your cathode anode here, these ions that seemingly floats around are still under the influence of these electric charges, right? Okay. Oops. So here we have electroosmosis. Now what happens is, right, because we analyze that the charge of this silicate is highly dependent on the pH here, so you see that, remember EOF, the electroosmotic force, right, mobility gets higher and higher in a higher pH. Remember that over here, right, when at the pH 9, most of the silanol is fully ionized, which means it becomes O minus. When you have O minus here, then you have your double layer, remember, in the zeta potential, so that after that you have a lot of all this electroosmotic flow, right, which is something that's not so desired, yeah, but it's there. So remember this, and more of understanding the reason. When we have a low pH, all these silanol groups are they are protonated, so there's no charge. So when there's no charge, how can you have a thick layer, right, the double layer, and how can you have a high amount of this EOF mobility? Think about it. So in a more illustrative diagram here, you can see that the anode is a positive charge, right? So the anions are drifting to the left and the cathodes on the right side. So you have this collision of these ions here. But what happens is, right, because of the influence of pH there, right, the silicate either becomes O minus or OH, and this affects the thickness of the double layer. Okay, remember that. Okay, and so it affects this amount of electroosmotic flow. Right. So here you see that when you have a normal EOF, right, normal, you have in general this kind of a movement of the ions, the opposite charges, right, move this way. Now here, this is a comparative diagram where it's solely as a function of charges, right? Electroosmotic flow profile is, right, you see that this is a vertical line, so here's a cross section of the capillary. Even ions closer to the walls of the capillary will move at the same rate because it's solely due to charge. But this is under a very realistic, idealistic assumption, right? The thing is, we know that near to the wall, there will be some kind of friction, right, and also kind of collision. So, but the thing is, it's minimum because we have a charge that's a larger factor. So the driving force for the movement of ions in CE is really due to the charges. Okay, there's no or very little pressure drop by the side. Okay, so the flow we can assume and consider to be more uniform across the capillary compared to when we use a hydrodynamic flow, something similar to maybe HPLC, high performance liquid chromatography, not capillary electrophoresis. Okay, then there will be a significant amount of the friction forces by the side. So which means that the particle drift in such a manner, right? Which means that here I find some x-axis really, it deters around all this part here, okay, and some effect later. What effect is, remember you have this a sensor, a detector right at the window, very narrow window, and if you have a hydrodynamic flow profile of a sample, it means that I can count 1 second, 2 second, 3 second, 4 second, right? It still passes through, you see my camera, right? Because of this hydrodynamic flow, maybe 4 seconds I can still detect the same thing. Compared to the electroosmotic flow, I can do this. You get it? What does it mean? Band broadening. You can see that. Here on the right side is small, you see? It's not really straight, but just a little bit, okay, compared to your liquid chromatography. You see, band broadening. But for C, the peaks are really narrow and sharp, and this is more reproducible, okay? So this is the real advantage of CE, sharper flow profile, higher separation efficiency. You don't want to have a very, very broad peak and not sure whether it's an overlap of two peaks, right? CE minimizes the chance. So here's a more representative comparison because this is taken from an actual chromatogram. Okay, electrophoregram as well. You put it together, juxtapose it for the same sample, and we can circle back to the plate theory here, the number of theoretical plates here, and the same formula you see last time. Because of this, you have your signal, there's a triangle, and then you have your width of the mid of the peak, right? So C give a better separation, right? Even if you have the same difference in the migration time between the signals. So even when you have a good resolution between two peaks, there's no overlap of the peaks, but because of the lack of or the minimized band broadening here, using the number of theoretical plates, you have a high number of plates for CE compared to your HPLC. Okay, just because your peak width at half-light is so much narrower. Okay, so therefore I will choose C over HPLC for better separation efficiency. Okay. Next, some calculations. You can just put some substitutions if you are asked to calculate. It's an electroosmotic mobility. We call it the mu EOF or mu EO here, right? So it's just your zeta potential as a product of the dielectric constant over the 4 pi nu, okay, the viscosity of the buffer. And how do we change the viscosity of the buffer? We know that water is not very viscous, right? But if you have something like a ionic liquid, something that's very dense and packed like your honey or pipa gao, these are very viscous. So it's about what substance we have inside. Of course, if it contains a lot of ions, very viscous, high number. Okay. But something to note is that the mobility of the electroosmotic force is only dependent, right, of the buffer characteristics as I've described, and is independent of the applied electric field. So you can spam a high voltage for electric field, it has got no effect. Next, we calculate the velocity of electroosmotic flow, right? We call it the VEOF. Now, why velocity is important? Remember the first couple of slides. C is really about the function of how fast the movement, right, between the two terminals of the cathodes, of the anodes. So here you see that the calculation is given by this, and the E here, not the epsilon, is the E. Capital E is the applied electric field. So we consider the voltage divided by the length of the capillary. Because when you have a longer capillary, you have a longer runway. Longer runway means you're able to separate more, right? You can let him run and see, oh, who's faster and who's slower. And this equation is called the Helmholtz-Smoluchowski equation. And if it's not capillary, there's no the 4 pi. 4 pi because when you do the pi r square and then you do the first derivation, right? And then you have a 4 pi because it's circular capillary, but that's for the math. The key point to note from here is really that the velocity of the electroosmotic flow depends on the applied electric field. So when you increase the voltage from 100 kilovolt to 300 kilovolt, the ions are going to move so much faster because of a high velocity. Okay? And this velocity is also dependent on the buffer pH because pH has a amount of H plus ions concentration. The buffer concentration, organic solvent, and the surface of the capillary. So it's all intertwined. Now besides, right, so we have the talk about the electric applied voltage here. The higher the voltage, right, the higher the EOF. So what does it mean? That means your migration time becomes lower because you can move faster. Of course, the time taken is shorter, right? Which means you have a faster separation. But does it mean when you have a faster separation, then the peaks will overlap? Think a little bit more, okay? Now, when we raise the voltage, you also increase the separation efficiency. Because if you are able to separate them, and as long as they finish the race faster, you don't waste so much energy, which means you don't clog the heat there, right? So it provides the Joule heating of the buffer solution dissipate more quickly, okay? Because you don't want to halfway in the race or separation that, oh, there's heat build up and then you have some kind of diffusion due to heat movement, and then that affects the separation. And you know that heat causes your eddy current and your convection or even formation of bubbles. Why bubbles? Because if you have something that's very volatile in your organic solvent, then it becomes vapor, right? So you want to avoid those. And the Joule's heat here, this undesired, is very proportional to the power in watts here, right? So P equals to VI, voltage, potential difference, and the product of the current. So the maximum voltage that can be used in C is calculated from the Ohm's law plot. You know the Ohm's law, you have your Y against X axis, but an instrument only follow Ohm's law, right, if it's directly proportional. So after this maximum voltage here, it doesn't follow Ohm's law, and then you shouldn't do that because we cannot anticipate how steep it's going to turn, okay? And how do you measure that? You're going to do testing. That's why we have research experiment. So we can see that when we apply the difference voltage, right, on the same sample without changing pH, we just change the variable called the, you see the applied voltage, when we increase the voltage from 10, 15, 20, 25, 30, here you see that the separation is still there. There's no overlap of peaks. But we reduce the separation time, so we save time. When we save time, we can run more sample, we can have a high efficiency, okay? The other thing is it's also allow for sharper peak because the peaks will be condensed, okay? Voltage too low, then people ask what are the benefits? You save money, right? I don't use so much electric current here. It takes a time, but then you may have some peak broadening, and this might be good sometimes when you have a very complex sample that's too many signals that's very close here. So we'll always do some testing and see we find something of the middle ground here, okay? But in general, we seldom use 10 kilovolts unless the country is down and there's a call on saving electricity, okay? So you notice that here we show a trend. In 10 kilovolt here, the peak 5 is not shown. There's no more peak 5 because it's too far away, right? And if we set the setting of the scan to be half an hour, it's not even there. Then we think that there's no fifth compound, there's only four molecules, right? So therefore, if you can try to have a higher applied voltage, okay? And this is a mixture of some amine particles like thiamine, HCl, niacin, pyridoxine, niacinamide, neutral particle, and cyanobalamin. When we present electrophoregram, we always indicate the buffer concentration. What does it consist of? In this case, it's sodium tiodecyl sulfate. Concentration of the co-buffer, right? So your surfactant, sodium borate, pH, exact pH to 2 decimal places, in dissolved in what? Capillary, is it what? Fused silica, right? Burn. The bore, the diameter of it, okay? Internal diameter is ID. The length of it, and the detector, UV, fluorescence or something, right? At which wavelength are we measuring? And the temperature, because all these are going to influence the outcome of your electrophoregram. Okay, next part here, we analyze the effect of buffer pH on EOF. So we talk about, remember your fused silica has a lot of your silicate O minus, right, attached to Si, but in a very low pH where we have a lot of H plus here, then you can protonate on the O minus and form your Ceylon null, right? Surface that's uncharged. Now, let's do a recap. The EOF increases with pH. High pH, high amount of hydroxide ion, silanol gets deprotonated, you form more your silicate O minus. More of the O minus here, it becomes charged surface, you have a double layer, and that's why you have high EOF. Okay. So again, we'll present also the properties of this electrophoregram here. Okay, you see difference between Teflon polymer, your polytetrafluoro, okay, ethylene, PTFE, versus Pyrex, yeah, pseudo glass, okay, compared to silica. So, effect of buffer, besides changing the zeta potential, right? So we mentioned this actually. Just to recap, at the lower pH, right, you have more neutral properties and less surface ionization, lower zeta potential, right? And there's a limit. So below pH 2, virtually there's no UF because it's virtually all protonated. Okay. Now what about inorganic buffers here? So inorganic buffers are like sodium chloride and ions, right? But let's talk about sodium tetraborate. The electroosmotic force, right, decreases with buffer concentration. So you see when you have a higher concentration, the EOF becomes smaller here, right? So in this case, we use a neutral marker to measure the electroosmotic flow. Because if you don't measure this, right, you don't know what's the starting point. It's like when you run a race, you want to bang, you want to see where are they starting. You need to have a marker there. Okay. So in some instances, we use this beta naptor to indicate a marker before we run the sample. Another kinds of inorganic buffer we have is the phosphate, right? Phosphate. So we have a plot here that talk about the long ionic strength. The higher the charge is the inverse linear relationship. So in a silica capillary, when you have inorganic buffers like phosphate, pH about 8, right? Then you see that as your ionic strength, right, law of the ionic strength, right, increase, your EOF decreases linearly. Okay, so of course when you want to do a exponential of this to remove the inverse function of the ln, then you see a curve, right? So I just want to highlight that this square here in terms of phosphate, PO3 minus, circles is borate, right? And then your triangles are your carbonate, CO32 minus. Okay. Here, okay, we have different kinds of your analyte here, right? Different kinds of ionic strength, but these are organic buffer, you notice. And how do we see the long names? Like 2,2-amino 2-oxo-ethyl-amino ethanol, ethane sulfonic acid. Don't need to memorize them, okay? But I want you to understand that independent of your organic or inorganic, right? As long as your buffer ionic strength increases, right, then the EOF decreases linearly in this manner. Okay. So if the temperature is constant, okay, and we just vary the variable of a buffer concentration, it results in lower EOF. The reason is that because when you have more ions, right, it will shield the surface charge of the silicate here. So that means there's less protonation, and then you have a lower EOF, right? There won't be any residual ions there. But if temperature is not controlled, right, inside C, we remind ourselves that there's also a little refrigerator. You have some conditioning. Because you want to control, you must have some aircon to the heat dissipation, right? The Joule's heating. So we need to make sure that it's consistent at the sometimes low temperature, like 0 degrees Celsius, for some sample that will decompose at 25 degrees Celsius. So in this case, when the temperature is not controlled, then when you have a higher buffer concentration, it will have an increase in EOF. Because when you have a higher current, right, of course, more current means you have a more flow of electrons. There's a higher temperature it generates, and then of course you have a lower viscosity. When it's a bit more dilute and less viscous here, there's a faster flow. Faster flow means you have some EOF. So another effect is your Joule heating, right? It's really a consequence of the resistance to the flow of the current. Remember, we talk about the flow of electrons, right? The rate is about current, the current, And when we look at the P equals to IV, and we can change to I square R. This is the resistance of the flow of the particles. So if the heat is not being dissipated from the system right enough, right, there will be residual heat inside there, and that causes some kind of broadening, because you have ions with energy, and then they'll just vibrate and move and translate, and that reduces the separation efficiency because they're still there. They're under the influence of your heat, right? Not solely due to charge. So therefore, heat dissipation is very important for a very good C separation here. Okay, so now we talk about when you have a narrow ball here, very small, very fine ball of CE, right? Then you have a very large surface area to volume ratio, which is preferred. Okay, so you can do some simple substitution, right? That if your internal surface area is smaller because of a lower diameter, you have a faster rate of heat dissipation. So therefore, we prefer to use a higher applied voltage. Okay, if there's a opportunity to have a faster heat dissipation.